Alright, so in this question, what we're asked to do is solve for the transfer function g, which is equal to x2 divided by f. So x2 is the displacement of this cart here, and f is the applied force on the end. So to start this off, what I'm going to do is draw the free body diagram of each of the different masses in my system. And I have two masses, which is why it's a 2 degree of freedom system. So let's start with drawing the free body diagram of the first one, M1. So isolating the mass itself and drawing the forces onto it. So let's start with looking at these two components here and the force they're going to put onto our cart. So the force here is going to the right, so let's assume that this mass gets picked up and moves to the right. What we would expect is that these two components here are going to resist that change and try and pull it back to where it was. So they're going to go to the left. Now the size of the force that acts through the spring is proportional to its displacement. So it's going to be the spring constant multiplied by the displacement, or how far the spring changes in length, which is going to be equal to how far this cart moves. So x1. Same kind of deal for the damper, except that it's relative to the velocity. So since it's attached to a wall, it's going to be essentially how fast this cart moves, which is c k1x. Alright, so now we can deal with this component on the other side. So again, I'm going to assume that this mass gets picked up and moves to the right hand side, and if we just ignore this for a second, what we would again expect is that the damper is going to push it back to where it was. So it's going to go this way. So it's going to be equal to the constant for the damper multiplied by the velocity that the damper is moving at. And the only kind of complicating factor is now, instead of being against a wall, we're actually against another mass which is capable of moving. So what we need is the difference in the velocity between the two carts, because that's going to be how fast our damper is moving. So this one goes to the right, so it's going to be at some speed, which is x1 dot. And this one has the potential to move as well, so we need the difference. So it's going to be minus x2 dot. Alright, so the last thing that needs to go in our free body diagram is the mass times acceleration term. And again, I've said this is moving to the right, so the inertia, or the mass times acceleration, should be to the right. And it's going to be equal to the mass multiplied by the acceleration of that cart. So that's the complete free body diagram for the first mass. Now we'll move on and do the same kind of thing, except for mass 2. Alright, so isolating out the mass again. So let's start with this force here. So this is the applied one. We're given its direction. So it's really just a matter of drawing it on. And I'm going to assume again that this is going to move to the right. So if this moves to the right, again, this is probably going to try and pull us back. And we need to multiply by the difference in the velocities of the two carts on either side. So it's going to be this time x2 dot minus x1 dot. Okay, so this one moves at some rate to the right, and then this one has the potential to move as well, so we need to take the difference between them. Alright, so the only other thing that needs to go on is the inertia term. Again, I've said that this is going to the right. So it's going to be m2 times x2 double dot to get the acceleration. Alright, so now what we need to do is develop the equations of motion. And for these spring mass damper systems, we need to get those equations from summing the forces on each free body diagram. So we're going to end up doing this twice. So all our motion is happening in the x direction. So we're going to sum our forces in the x direction, and I'm going to treat as to the right as the positive direction. Now the way I've drawn it, all the solid lines for the arrows relate to the left-hand side of the equation, all the dotted lines here relate to the right-hand side. So let's go ahead and sum it. So we're going to have negative kx1, negative c, I think this should have been c1, yep, x1 dot c2. Okay, so they're all in the negative direction, and this one's in the positive direction on the other side, like so. Alright, same thing down here. So we've got negative c2, positive f. Again, this is for the right hand side, it's in the positive direction. Cool. So now we have our two equations of motion, and what remains is rearranging these equations to get the transfer function that we're interested in. So we eventually need to get this to look like x2 divided by f. Now you can see that here we've got them as functions of s's. That tells us we need to take the Laplace transform. And the reason we're going to do that is because at the moment all of our x's are tied up in time derivatives. So by taking the Laplace transform, we get rid of those time derivatives essentially, but they get replaced with the s's. And then we can just treat the x's on their own with regular algebra. So let's take the Laplace transform. We're going to assume that all the initial conditions were 0. So this one here, k is a constant, x1 is a function of time, so it's going to become a capital. c1 is a constant, x1 again is a function of time, it's got a derivative, so that means it gets 1s when we transform it. Alright, this one here, they've both got one derivative, so each of them is going to get an s when we transform it, and I'll just stick it outside the bracket. And this one, it's got 2. Put it in front, so it's going to get s squared x. Okay, so that's the Laplace transform. Let's go ahead and do it to this other one, again assuming all the initial conditions are 0. So these both have a dot, so that means they both get an s. And I'm just going to put that out the front, factorized. We know that f is a function of time, so when we Laplace transform it, it's just going to go into a capital of itself. And this one gets an s squared. Alright, so now we can treat the x's on their own. Sorry, this one's lost its one. And what we're trying to do again is to get x2 divided by f. So you have a couple of options at this stage. You can solve these equations simultaneously by substituting them into each other, or alternatively you can use the matrix method in order to solve. So that's the one I'm going to opt for in this case, but either one will work, and not one's particularly harder than the other for these 2 degree of freedom systems. They're usually pretty similar in terms of difficulty. So in order to put this into matrix form, what I want to do is put everything with an x on one side and everything without on the other. So let's start with this one here. I think everything actually has an x in it. So we're going to get a 0 on one side of the equation. I'm going to shift everything else to the other side. Okay, and now what I want to do is factorize out each of my unknowns, so x1 and x2. So starting with x1, so we've got m1 s squared, we've got a k here, and we've got c1 s, and we've also got c2s. Alright, so then we want to factorize everything that's got an x2 in it, and I think all we've ended up with is this bit here. So I'm going to put minus x2 c2s. Alright, same kind of thing on the other side, for the other equation. We want the constants on one side, everything with an x on the other side. So let's leave the f, and move this over. Sorry. Okay, and I want to factorize again. So I'm going to take out a negative x1, and you'll see why in a second. This is the only thing that needs to come out. And then we're going to have plus x2. And we get that. Alright, so these are some linear equations that we're now able to solve by putting them into a matrix, as I said. So the form of the matrix is AX equals B. A is your matrix of constants, which are out the front of each of your unknowns. So this and this and this and this. X is the matrix of unknowns, so we want to know what x1 and x2 are. And B is the matrix of the constants on the other side of the equation, so it's going to be the 0 and the f. So let's go ahead and put this all into the matrices. So starting with the A matrix, just going to change this around to make it look more conventional. Usually you put the mass term, then the damper terms, and then the spring terms. Okay, this one is negative C2S. So this one related to the x1, this relates to the x2, and then on the other side our constant is 0. So now we just need to do it for the other one. So in front of the x1 we have this, and x2 we have this, and the constant on the other side is f. Alright, so that's the matrix that needs solving. Now just before I move on and actually solve it, I just want to show you a bit of a trick with how you can have a double check, I guess, at this stage to ensure that you have the right things inside your equations. So, alright, so I've just copied down our original question down here so we can see it at the same time as the matrix. So, what I want you to see is the pattern. So if we look at the M1, what we end up with in this first cell, I guess, is that we've ended up with the mass term and we've ended up with both of the damper terms, and we can see that they're both attached to M1, and we've also ended up with the spring term, which is attached to M1. If we go down here to the bottom cell, what we can see is we've ended up with the mass term, M2, and we've ended up with C2, which is the one that it's attached to as well. Okay? Finally, if we look at the diagonals, what we ended up with is the negative of the component which is in between M1 and M2. Okay, so there's a bit of a pattern emerging. And on the other matrix on the other side here, we can see that we have no value in here, which is the one related to mass 1. And we have F here, which is related to M2, and we can see that it's the external force applied onto it. So, if you didn't already pick up on it, this is the pattern that we should see in these basic spring mass damper systems. So we should end up with the positive of everything attached to M1, including M1 itself. So by inspection, in order to check that you've done this correctly, we should have M1, C1, C2, and K terms in this, and they should all be positive. Down the bottom here, it's going to be everything that's attached to M2, and it's going to be positive. So we've got M2 itself and C2, which we saw before. And these on the diagonal need to be the negative of what's between the two masses. So again, the only thing that's between them is C2. Okay, so finally on the other side of the equal sign, we have the forces which are externally applied onto our masses. So we can see we had no externally forces applied on M1, so that's why this cell was 0. And we have F here applied onto M2, so that's why this cell ended up as F. So I definitely recommend you double checking when you get to this point that you've picked up all of the terms that you should have and you have the correct signs on them that you should have as well. And I should mention that that method works for larger degrees of freedom systems as well. So now let's jump back to actually solving it, since I've confirmed that I have all the right terms in my matrix. So we were looking for the transfer function x2 on f, so that means that I'm going to need to solve this system of equations for x2. And to do this from the matrix method, we use Cramer's rule. Alright, so for Cramer's rule, we need to set up two matrices. One goes on the numerator and one goes on the denominator. And we're going to take the determinant of these matrices. So the one that goes on the numerator of our equation is going to be a form of this first matrix, the A matrix. What we want to do though is, since we're solving for the second variable, this is the first one, this is the second one, we need to put this matrix on the end into the second column. Okay, if we were looking for the first variable, so solving for x1, we would put this one into the first column. Okay, so we're looking for x2 in our case, so this is going to go into the second column. So let me just copy it out. Sorry, putting this into the second column, so 0 and f. Okay, on the denominator, what we do is just copy this A matrix down. It's a bit messy. Alright, so now we just need to go through and solve the two determinants. So for a 2 by 2 matrix, the determinant is AD minus BC. Okay, so these two get multiplied together. Minus these two, 0 times this is 0, so I'll just leave it off. And again, we need to multiply these two together. Minus these two. And they're the same, so I'm going to square it. Okay, this is x2 just getting carried down. So remember that we're looking for x2 divided by f. That's our transfer function. So I can get that pretty easily now. F is on the top line. If I divide it to the other side, we end up with x2 on f. So technically, if we stopped here, that would be our transfer function. However, what I'm going to do is expand out this bottom line, and the reason is you're going to find that things cancel out. Also, in the future, when you want to go ahead and use your transfer function for other things, you're going to need to simplify this bottom line down anyway. So let's get some practice at it, I guess. So unfortunately, all of this needs to get expanded out. So multiplying out these brackets gets a little bit messy. Okay, I think that's what we get. This gets carried on because it's very long on that bottom line. So what you should find is when you expand out these type of questions, whatever falls out in the minus bit on the end here should cancel with something else that was in the bottom line of the equation. So in our case, there's only one term that fell out on the end, and if we look back, we should be able to find a matching one, and in this case we can. This one's positive, this one's negative, so they're going to cancel out. Again, that's just a bit of a double check to ensure that you've expanded out everything correctly. So now what we can do is kind of write the final version, I guess, of our equation. And what I'm going to do is try and simplify this a little bit. So for the s to the 4 terms, we just have m1, m2. S cubed, I think we have a couple of things. C2, M2. Oh, sorry, got it on the front there. All right, S squareds. We have this one here. And in the S's, we have just this one here. Oh no, in this one. Sorry, I've made a silly mistake multiplying this out. Should be C1, C2. This term here should be S squared. So let me just go back and correct that. And this one is just the only constant, S term on its own. Alright, so that was very long-winded, but we finally got there. So that's the final answer for our transfer function, and it's now in a usable form with each of the different powers of s separated out. So that's all there is, and I'll see you in another video.